Okay, so now we come to a real exciting point, at least for me, and that is, suppose someone gives us an identity and asks us to prove whether that identity really is true or not, if it's a fact or if in fact it's fiction and in fact the identity is false. And the way to tackle these things is to use all the simple identities that we've already established, using the Pythagorean theorem to get like sine squared plus cosine squared equals 1, tangent equals sine over cosine, and so forth. And what you do is, if someone hands you this potential identity, the way I think about it is drawing a line in the sand, just drawing a line right through that equal sign, and manipulating one side, and then manipulating the other side independently, and at the end of the day coming up with two quantities that you know are the same. If you can do that, then every single step must be also equal, which means the original things must be equal. So the strategy always is to draw a line in the sand, manipulate one side, boom, manipulate the other side completely separately, and then hope that those two things at the end yield the same value. Let me try to illustrate this with a whole bunch of examples. These, by the way, are really my all-time favorite kind of stuff. So bear with me if I start to break out in song. Okay, so tangent x plus cotangent x. And the question is, does that equal secant x times cosecant x? Just barely slip in the x. Whoop. Okay? So I want to see if these two things are equal. So what I do is I literally draw a line in the sand here. Why do I draw a line, by the way? It's just to remind me that I can't think of this as an identity because I haven't proved that yet. So I can't add something to both sides and manipulate and go back and forth, because that's then assuming I have this. So I've just got to work with this, just have to work with this, and then hope at the end of the day the two things are equal, and then I can go backwards and say, oh, these had to be equal too. All right, so now where would I begin? Well, my standard strategy, it's so naive and stupid, I'm embarrassed to say it, but it's the truth, is I just convert everything to sines and cosines. Or at least I start off that way until I get to something that's easy to see. So here, for example, I convert everything to sines and cosines. So here I'd write this as, so then this is going to equal, this side here, this side, I know equals sine x over cosine x plus, and cotangents, it's reciprocal, so cosine x over sine x. All right, I've got two fractions I'm adding up, so I'll get a common denominator. That means I'll multiply top and bottom here by sine of x, and I'll multiply top and bottom here by cosine x. So I have a common bottom. So then I see, well, if I multiply top and bottom here by sine x, I'll have a sine squared x on the top over sine x cosine x, plus, and then over here, when I multiply top and bottom by cosine x, I'll have cosine squared on top, and then the same bottom, sine x cosine x. The bottoms are the same, so I can actually add and see sine squared x plus cosine squared x all over sine x cosine x. But what's sine squared x plus cosine squared x? Well, from the trig identity, the Pythagorean theorem, we know that's just 1. That's always 1. Sine squared x plus cosine squared x equals 1. So in fact, this just equals 1 over sine x cosine x. So I saw what this complicated thing equals just in terms of sines and cosines. Let's do the same thing now on this side. So now I'm just going to use this side here and say, well, this equals, well, what's secant? Secant is 1 over cosine x. Cosecant is 1 over sine x. So what do I see? I see that this equals 1 over the product of these things, which I could write as sine x cosine x. And now what do I see? What I see is the left-hand side ends up equaling this. The right-hand side ends up equaling this. These two things are the same. That means these things must be equal. And I just proved this identity. Okay? So the way you prove the identity is to work on the left side, work on the right side separately, and then get two things that are actually equal. If these are equal, that means that these are equal, which means that these are equal, which means that these are equal, which means that these are equal. So I proved the identity. I just love this. I do love it so. Okay, let's try another one together. How about tan x plus secant x equals cosine x all divided by 1 minus sine x. Let's see if that's an identity or not. So I draw a line in the sand. and I'm going to now massage both sides to see if I can make them look the same without crossing that line. So just on this side here, what would I see? Well, this equals, and again, all I do is convert to sines and cosines. It's so naive, but it works. So sine x over cosine x plus, and what's secant? Secant is 1 over cosine. And so now these two things are equal. And so what do I see? I see sine x plus 1 divided by cosine x. Okay? So that's what I see on this side. And, well, it sort of looks like this a little bit, but not exactly like this. So this is sort of a little bit annoying. You'd say, gee whiz, I sort of wish that these things would look exactly the same. So one trick that we could sometimes perform just to sort of see if we can sort of get these things to look the same is to say, well, it doesn't look the same to me right now. So maybe I should just multiply this top and bottom by a very clever choice of 1, right? If I multiply this by 1, of course, nothing changes. Now, can I think of a very clever choice of 1 to multiply by? By the way, I'm going to just draw this here so I can write out some stuff here for you to see. Well, sometimes, you know, in life and in math, when you're dealt a hand that's not what you want, you should try to sort of reshuffle the deck and try to see if you can fix the hand. So in this case, the denominator I would really fantasize about, like in my wildest dreams, would be 1 minus sine x. That's the fantasy denominator. Well, why don't I just sort of fix things by putting that denominator in? Now, I know what you're saying. You're saying, whoa, Berger, if you're going to do that, you're changing the value. Well, you're right. But what if I also do it on the top? See, then they cancel. It's just 1, and I don't change the value. So I'm picking a very clever choice of multiplying by a 1, and the 1 is going to be represented in this very eclectic way, something over itself, where the something is the denominator I really would love to have here. So I'm not changing the value of anything, but it's a clever little trick. Now on the top, I've got to be careful, and I've got to FOIL that out. When I FOIL that out, what do I see? I see sine x as the first term. Then my inside term gives me a plus 1. My outside term gives me a minus sine squared x. And the last term gives me a minus sine x. Now on the bottom, remember in bottoms we hate to multiply things out, so I'm going to keep everything just as is. I'm not going to distribute or anything. Now notice something really cool happens. I see a sine x and a minus sine x. So they actually add to give 0. And then I see a 1 minus sine squared. So what is 1 minus sine squared? Well, go back to one of our famous trig identities. This one, sine squared theta plus cosine squared theta equals 1. So what's 1 minus sine squared? Well, if I bring this over, sine squared, I see 1 minus sine squared, that equals cosine squared. So in fact, I see that top, what's left over, is just cosine squared x over that bottom. Cosine x times 1 minus sine x. Let me write that in here so it's clear. What I'm left with here is cosine squared x divided by cosine x times 1 minus sine x. But notice I have 2 factors of cosine on the top, 1 factor on the bottom, so I can cancel this factor on the bottom with one of these factors on the top, and what am I left with? I'm left with cosine x divided by 1 minus sine x. And what do you notice? Well, it's exactly this side. That's exactly this side. So I've just established that the left side and the right side are, in fact, the same. So these things are equal. Why? Because this equals that, equals that, equals that, equals that, which equals this. So I just proved this trigonometric identity by massaging just the left side. By the way, notice that when I came across the stumbling block here, I did not panic. But instead, I tried to force things without cheating by multiplying by 1. And the very clever choice of 1 I picked was something over itself, and I tried to force the problem knowing what I'm trying to prove. And that actually pushed me through. Great technique. Don't panic in life. Just try to see if you can work around the problem by putting the thing in and then just taking it out. We'll take a look at a couple more examples up next. These things are sort of really fun, but a little bit tricky. You got to take it easy, take your time, and you can do it. Enjoy.